Hi, my name is Mateus Sfeir. I'm going to be showing my assignment 4 on reducing overfitting in ConvNets of my course of machine learning. So here I'm importing the necessary libraries for this project. I use TensorFlow and Keras to build and train the neural network and Matplotlib to visualize the results. Here what we see is I load the CIFAR-10 dataset, and then I normalize the pixel values by dividing for 255 so that all values are between 0 and 1, which helps the model train more efficiently. After that, I split the dataset into trainer and validation sets. I also reduce the dataset size to speed up training while still keeping enough data to demonstrate overfitting. Here we have the image, so all of the images from the dataset can be visualized. This helps visualize what kind of data the model is learning from. The dataset contains different categories like animals and vehicles. In this part, I built my first convolutional neural network, which includes convolutional layers followed by pooling layers and then several dense layers. This model is intentionally large with many parameters, which makes overparameterized. An overparameterized model can easily memorize the training data, which leads to overfitting. Here I trained the overparameterized model using the trained data. I also use the validation data to monitor how well the model generalized during training. I trained the model for 10 epochs, which was enough to clearly observe overfitting behavior. Overfitting accuracy. In this chart, the training accuracy increases very quickly and becomes very high, while the validation accuracy improves more slowly. This gap between training and validation accuracy indicates overfitting. Overfitting loss graph or chart. This chart shows the loss values. The training loss keeps decreasing by validation. Loss starts increasing after some point. This is another strong sign of overfitting because the model is no longer generalizing well to new data. To reduce overfitting, I built a second model using regularization techniques. I applied Dropout, which randomly disable neurons during training, and L2 regularization, which penalize large weights. These techniques help the model simpler and improve generation. Train regularized model. Here I trained the regularized model using the same dataset and numbers of epochs. This allows us to compare it directly with the overfitting model. This chart, we can see the gap between training and validation accuracy. It is smaller compared to the previous model. This shows that regularization helped reduce overfitting and improve generalization. In this section, I define data augmentation techniques that includes random flipping, rotation, and zooming of images. This helps create more diversified training data and prevents the model from memorizing patterns. Here I built a third model that includes data augmentation as part of the training process. This further improves the model ability to generalize the new data. Train augmented model was used with the same configuration and it helped us to make the model learn more robust features. In this chart, the validation accuracy is more stable and closer to the training accuracy. In some cases, the validation accuracy can be slightly higher due to the effect of dropout and augmentation. This indicates the model generalized better and overfitting is reduced. So, in conclusion, I demonstrate overfitting using overparameterized convolutional neural network. Then I reduce overfitting with dropout, L2 regularization, and data augmentation. These techniques improve the model performance on validation data and help it generalize better. I also found that around 8 to 10 epochs were sufficient to achieve good results.